So there's an entropy specific for the substance and the temperature and and its um, its composition. So also we're going to have a performance degraded by irreversibilities. So in a process we're going to have inefficiencies, and we can determine the efficiency of the system. And the greater the irreversibilities, the greater the entropy generation. So entropy generation can use to determine the quantitative measure of irreversibilities with a process. And we're going to have for pure substances the entropy change are going to be determined in we can find it in the property tables. And so a process that has a constant entropy value is going to be called an isentropic process. So this process is going to be an irreversible, internally reversible process, and it should be an adiabatic process as well. So now we're going to have diagrams such as the PV diagram, but in this case we have this diagram for heat transfer for processes internally or totally reversible. So the area beneath this line is going to be the heat transfer, and we can calculate it as delta as the integral of these two reference states, the temperature. And for isentropic processes, which is the ones that do not have any change in enthalpy, we're going to have only a line because there's no change in entropy. So now, what is entropy itself? Entropy can be viewed as molecule disorder. So when a system becomes more disordered, the entropy increases because the positions of the molecules are going to be become less predictable. So for if we have gases, the entropy is going to be greater than the entropy of solids, for example, or even liquids. And the entropy of a pure crystalline substance at an absolute zero temperature is going to be 0, since there is no uncertainty about the state of the molecules at that instant. And this is the third law of thermodynamics, which talks about the absolute entropy. So now we have the Gibbs equation. In this type of processes, the temperature varies, and it is applicable to open and closed systems. So now we have this formula, but we know that the enthalpy equals the internal energy and the pressure times the volume. So we can substitute this into this formula.